Okay, back again. So today we're going to start more serious work on quantum walks. We've done most of the algebraic machinery. Well, a large proportion of the algebraic machinery will need, although there's more to come. And we'll also need some number theory to go on. So what about quantum walks? Now, so we can think of quantum walks as a physical object, and there's an underlying mathematical model which the physicists give to us. So as far as the mathematics goes, there are really three parts to it. There's initial state, there's the transitions, and there's something about measurement, which actually won't bother us too much most of the time. So the simplest case and the most frequent case is what I call a pure state. So the density matrix, so states are given by density matrices. A pure state is given by a rank 1 density matrix. The rank 1 density matrix can always be written as the outer product of vectors, a unit vector Z with itself. Okay, you make it a unit vector, give you trace 1, and it's probably semi-definite for free. And with that assumption that if you're quantum walk, the state at time t is given by this. Now, I've already made a mistake because the physicists will want a minus t here and a plus t there, but it makes, so long as you don't change in the middle of an argument, it's okay. And no one's ever complained to me about it, or not had the nerve to complain about it. Some of my students follow this and some do it the right way. It's your choice. So this tells you how to get from what the initial state will be. Now, the problem is to get information, you don't actually see the state. What you get, you carry out a measurement, okay? And so I want to make a, well, and so I carry out a measurement. I'll get to it in a second. The thing I want to point out too is that this UTZ is a unit vector because UT is unitary. And so this is now the product of a unit vector with itself. And so this is definitely a density. Okay, so you've changed to a new density. Okay, now the measurement, well, I've gone through the strict formality here. So we have a POVM. So we have a collection of quasi-semi-definite matrices, QR, summing to identity with QR quasi-semi-definite. And this is called that a POVM. Okay, and so in our case, the QR is going to be just the transpose. So the terms of the POVM are the same as our initial states. Now that is just an accident. It's just the way things work. There's no sort of direct relation between the terms of the POVM and the initial state. In this particular case, in fact, this is the most common case, the terms of the POVM are exactly the terms of the possible initial vertex states. But you can have other initial states and you can have other POVMs, but let's not worry too much about that. And so the rule then is that to get the outcome of your measurement is a vertex of the underlying graph, which I haven't defined at this point, but we'll get to there. And so the outcome of measurement, and so in this case, suppose the result of the measurement is A. The question is, what is the probability of observing A when you do this measurement? And according to the axioms, this guy here, this inner product, it's going to give you a non-negative number, and that non-negative number is going to be the probability that you observe A. And so then I've done a calculation here, the inner product in terms of trace, use the cyclic property of trace to move things around, then observe this is just a product of two scalars. And so we discovered the probability, actually I assume we're starting at a state Z, the probability that we observe the vertex E sub A is given by this. So it's the square of the absolute value. And so the point is, experimentally, physically, in some sense, this is all you see. You don't have access to the entries of the state, other entries, specific entries of the state. What you have access is this. Okay. Now the UTZ is determining the state, and this is corresponding to measurement. Okay. And so your questions about entries of U of T, the physicists may say they're not physical. Okay. So, but you can get the squares of the absolute values, that is physical. Okay. So if our initial states are vertex states, which is they will be for a long while, and we start at EB, then the probability you observe A, according to the formula, just becomes the square of the absolute value of the AB entry of U of T. So I can compute the probabilities of the different, observing A, given that we started at B, from the squares, the absolute values of U of t, and it's often convenient to write this as U of t circle the complex conjugate of U of t, and notice that the complex conjugate of U of t is equal to U of minus t. And I guess we've done this before. The point here is that U of t is x of ita, and so this is unitary, and since A is symmetric, it's also symmetric, and that's why you get this identification between you get the identification between the complex conjugate and the inverse. Okay, that comes up a number of times. So, so in the simplest case, we can sort of forget about density matrices, and the information we need is just the squares of the absolute values of U of t. Okay, and U of t is just given by x of ita. So, okay, it's just linear algebra at this point. Actually, all quantum mechanics is just linear algebra. That's what causes the physicist problems. Now, it's useful to give a name to this shared product, and I call it the mixing matrix. Not exactly sure why. Well, it comes up when we talk about mixing, but it doesn't matter now. So the point about this matrix is just it's replacing the entries of U by the squared absolute values. So each row sums to 1, each column sums to 1 because U is unitary. And the entries give the probabilities of observing a given vertex, given you started at some other vertex. So all the information you can deduce by experiment, and in particular by measurement at time t, is contained in the mixing matrix M of t. Okay, so everything in M of t you can see, you can measure. Okay, and so that's what we, in a sense, we have to ask questions about M of t. If you start asking about whether the ij entry of U of t is 0, that in some sense is not a physical question. Okay, so so M of t is just a repackage, it's just a reduced form of the transition matrix. Now, if we weren't measuring in the standard basis and we're using different initial states, then this formula would have to be replaced by something more complicated. Okay, we'll worry about that when I need to. Any questions at this point? Okay, so let's start on an example. And so the simplest entering case is the complete graph on 2 vertices. And what can the Hamiltonian in this case is just the adjacency matrix to graph, which is a real symmetric rational matrix actually. Now the initial states, well, from a physicist point of view, they'll say the initial states are given by these two elements, the standard basis. I could take the outer products and get density matrices, but I'm doing that. I won't do that straight away. And so U of t is x of ita. And now this is one of the few cases where the series for exponential allows you to compute the exponential. Okay, because when you compute the powers of the 0, 1, 1, 0, the odd powers are just 0, 1, 1, 0, and the even powers are just the identity. So you do the obvious repackaging and you discover that the fact that U of t is equal to cosine of t times this vector matrix plus I sine t times this matrix, which I can package in a 2 by 2 matrix, and I'm abbreviating cos t to c and sine t to sine. Okay, so so this is okay, so this matrix is unitary, and it's giving us U of t as a function of t. In this particular case, M of t is just c squared s squared s squared c squared. Okay, and so the rows and columns sum to 1. So we prove that cos squared plus sine squared is equal to 1, in case you're in doubt. Okay, so we can, in this particular case, we can compute using, we get this explicitly. And we have the mixing matrix. Now, the point about the mixing matrix, the way to think about this is each column of the mixing matrix is well, the A column is the probability of observing A, given that you started a corresponding particular entry. The BA entry is the probability of observing A, given that you started at B. Now, so each column is a probability density, a set of non-negative numbers that sums to 1. Now, if you stare at this, okay, you get some complicated looking matrix. What can I learn about it? So the one thing that might occur to you is, well, what are the sort of the extreme cases? Now, I claim there are two extreme cases. One is when a column is a standard basis vector. And so your probability density is that you're always on the same vertex when you measure at time t. And the second possibility would be that all entries in that column of M are equal, in which case one vertex is as good as another. So you've implemented, in that case, if you've got that happening, then you've invented the world's most complicated dice with n sides, because it gives you the outputs number from 1 to n, and the probability that any one of them occurs is 1 over n. So I was saying the two extreme cases would be when the column of M of t is it's got one non-zero entry. Since the stochastic that must be 1. That means that it means that everything in that. Now the thing to remember is if U of t has got some number with absolute value 1 in a position, then since each row is a unit vector and each column is a unit vector, the remaining entries in that column and the remaining entries in that row are all 0. So having an entry in U of t with absolute value 1 is forcing a lot of zeros. And so correspondingly, it forces zeros in the Nixon matrix. Okay, so at the point right now simply is that having one entry in M of t equal to 1 is forcing a number of things to be 0. I mean, again, you see that because each row must sum to 1, and each column must sum to 1. So you can do it either from the unitary matrix or from the Nixon matrix. And in any case, what I'm saying is that the interesting cases would be, well, two of the obvious interesting cases are when a column, the entries of M of t are all equal to 1 over the number of vertices, which means that the corresponding column of U, the entries all have the same absolute value. And so we'll say a matrix of a complex matrix is flat if all its entries have the same absolute value. So if the entries of M are all got the same absolute value, then the entries of N, the corresponding column of U, is flat. We'll come back to that later on. So, so there are two extreme cases. Now, the most interesting is the first case where where some entry of M of t is equal to 1, because that's telling you no matter where you start, when you measure at time t, you'll see you're on. You'll get the same result, the same vertex each time. Okay. Now. So in that case, so if the BA entry is 1, then when you start it, I should say, but be more carefully, if the BA entry of U of t is 1, and you start at vertex B, or your initial state is on the vertex B, then the state at time t will be the vertex A, and you get the same result every time you do the measurement. So it's not quantum anymore, it's classical in some sense. It's not really classical, but the point is you always get the same result. Now, as I said, that's interesting from just an external point of view. It's also interesting to the physicists because it enables them, the underlying system for this quantum walk is a collection of n qubits, one for each graph. And so if you get this state transfer as I've just described it, you actually transferred the information from one qubit perfectly to another qubit after a certain time lag. Now, this is important because there's a theorem in physics called the no-cloning theorem, which basically says you can't copy a state. Actually, I might even let's say something like that. So the point is that we have some state. Let's think of it as D. Now, to create a copy, basically we need some quantum operations which take the state D and produce the state D tensor D. Okay, because a composite system in quantum mechanics is always a tensor product of subsystems. And so if we're going to copy, go from there to there. But now if I take alpha D, that would go to alpha squared D tensor D. And so this map is not linear. and all legal operations in quantum computing, path measurements aside, must be linear, like unitary. So this is telling you that you can't copy a state. Okay, so that's a bit of a problem for computing purposes because you often want to maintain copies of things. Now, what the state transfer we're just talking about says is that in some cases we can transfer the state of one qubit perfectly to the state of another. Okay, so this is one of the arguments why this question is interesting. So let me go on. This is summarizing my interesting cases. One possibility is that the B column of the MFT is just equal to the standard basis vector E sub A. Now, if A is not equal to B, in that case, we say we have perfect state transfer. Another possibility is that simply the MFT, the B column of the MFT is just the standard basis vector EB. In this case, we say we're periodic. And the third case is that the B column is a 1 over n times the all-ones vector. And in this case, we say we have local uniform mixing. Now, the perfect state transfer is the reason that probably the main reason that physicists, initially at least, were interested in quantum walks, in continuous quantum walks. Okay, so that was the where things started. As we'll see, that if you have perfect state transfer, you get periodicity forced on you. And so often it's when you're looking for perfect state transfer, it's easier to first try and identify the periodic places and then see which of those give you PST. And the local uniform mixing I'll come back to. But I mean, so it's generating perfect randomness, which is not a useless thing to do. And it has a lot of interesting combinatorial complications or consequences. So they're the three interesting cases: perfect state transfer, periodic, and local uniform mixing. And for the time being, I'm going to focus on the first two. And as I said, even if all you really care about is this, you're going to be forced to look at this. Now, there are other interesting cases. There's pretty good state transfer and fractional revival and things like this, but I won't be going into that for a long while if I do get to it. Now, for our walk on K2, we get local uniform mixing at each vertex at time pi on 4. So that happens. We get perfect state transfer at time pi on 2, and we get periodicity at time pi. So the periodicity occurs at time twice the PST, the perfect state transfer time. And that's the rule. In general, if you get PST at time tau, you'll get periodicity at time 2 tau. Okay, so these things go together. The uniform mixing, well, we have many examples where you get uniform mixing at half the PST time, and also we have examples where it's not. Okay, so it's not really clear when these two things should be related. I think most of them are related to cubes and quotients of cubes, but I don't know if Ada has an opinion on that. So if I write things out in terms of density matrices, which is what I prefer, now there's a number of reasons for doing this, but the basic reason is that I find by and large that working with the density matrices is easier than working with the unit vectors. Okay, and you'll see a lot of examples there. So generally it's easier. I mean, there are odd times when you want to use the others, but it's generally easier. If you're trying to get actual numbers out, there might be an argument sometimes that the projective version is a little better, but the general summary is that it's easier to work with density matrices than to try and work with the unit vectors. Now, if we, in terms of density matrices, I was having vectors, there's two standard basis vector, and the first standard basis vector is going to give me this. The outer product of E1 is this self. And so we start there and we apply U of t, initial state, U of minus t, then we get this. So cos squared minus I sine cos I times sine cos and sine squared. Okay. And so you see that, for example, the trace of this is cos squared plus sine squared, which is 1, as it should be, because this is a density matrix, and this matrix is similar to this. So this must be a density matrix. It must have trace 1, and it must be Poisson semi-definite. And so I'll leave you to think about that last part. It's positive indefinite because you can write it as an outer product. So from this we can now work out, or from this I could write down various things, but the point now is, do I have it? If I choose, if I take the time, oops, I've got free choice at pi on 4, pi on 2, and pi. And so the interesting time for us at the moment is pi on 2, because then you're going to have cos pi on 2 is 0. And so you get 0, 0, 1. And so if your initial state is this, and you're looking at the continuous quantum walk on K2, and at time pi on 2, your state is this. And so you've transferred the state. And so this implies that you've transferred state from vertex 1 to vertex 2. Now, we don't have the state of vertex 1 explicitly in front of us anywhere. There's a level of detail which I'm not going into, but the point is, so we've transferred from one vertex state to another vertex state, so we get perfect state transfer. At pi, so cosine pi is, I don't know, we're squaring everything, so all right, so this is all 1, and 0, 0, 0. And so there we have the periodicity, and I'll let you work out the pi and 4. So for the continuous walk on K2, we observe 3 phenomena. We observe uniform mixing, perfect state transfer, and periodicity. Any questions at this point? Okay, so, well, we followed the tradition and say, well, we worked out what happens for P2. What do we do next? Well, the next thing to think, okay, the next graph which is going to come up is going to be the path on 3 vertices. And I'm not going to go, this is worked out in the notes in detail, and so I'm going to refer you to that, but I'm going to go through some of the key steps. The first thing is that I can compute the characteristic polynomial of P3 using the one sum formula, because there's the one sum of actually 2 copies of K2. So you can compute this using the one sum formula. Okay, and so there's the characteristic polynomial. And so the eigenvalues at -2, 0, and √2. Okay, so we have the eigenvalues. Now we have the eigenvectors, and I've written them down here. So those 3 things are the eigenvectors. Now I could just say that I computed them in Sage, which I didn't. But so there's lots of ways of arriving at it. Since I went through and gave you the recursion for computing the eigenvalues of the path length vertices, I'll use the same argument. If I have suppose I have an eigenvector for P3. Now I know that it can't be 0 on the first vertex, because that would imply it's to be 0 all the way along. So I might as well, since I can scale it, I'll assume the entry on the first vertex is 1. And now let's suppose we look at the easiest case, look at the eigenvalue 0. So then 0 eigenvalue times this must be the sum of the weights of its neighbors. So 0 times 1 is 0. So this must be 0. Okay. So now 0 times this must be the sum of the weights of its neighbors. So this must be -1. And so there's the eigenvector. Okay. And you can do the same thing with the √2s, and you get this guy. And I guess I've left you this as a little exercise. So we get the 3 eigenvectors. The eigenvalues are simple, and so if the eigenvalue is simple, then and with eigenvector ZR, then the idempotent normalized eigenvector ZR is just the outer product of ZR with itself. So there's no particular trouble getting the idempotents when the eigenvalues of your matrix are simple. The other thing is sometimes useful. You may find that there's just one eigenvalue which is not simple. Then you just need to remember that the sum of the idempotents must be the identity. And so if you get the idempotents corresponding to simple eigenvalues, you can work out what the last idempotent is. But then I've computed the outer products of these 3 vectors, and so these are 3 idempotents. This is the sort of calculation I need to do 3 times until I get it right, and then take a vote. But I think I'm pretty sure it's the same result in the notes, so it must be right. So we've got the 3 projections, and if you stare at them long enough, you will see they sum to the identity. Okay, so I have the spectral decomposition. Okay, it's simple because I can, the graph's small, I can get the eigenvalues, I can write down those idempotents, and so there they are. And so now we can say that U of t is equal to the eigenvalue. Get this sum. It's worth noting because we have this eigenvalue 0, there's nothing to worry about here. This is constant. Now the thing to note is that pi on root 2. So pi on root 2, if t is pi on root 2, this is e to the pi I, that's -1. So you get minus, at time pi on 2, you get minus E1 plus E2 minus E3. And when you look at those matrices again, you discover this has got this form. So it's a permutation times -1. Okay. And from this, it follows that you're going to get perfect state transfer from vertex 1 to vertex 3. Now, when I use the term follows, I'm usually implying there's a little bit of work involved. I'm not claiming it's entirely obvious, especially if you're new to it, but you can work that out. Okay, so it's a reasonable exercise to convince yourself that if at the time pi on root 2, we get PSD. Okay. Now we've got signs in here because I'm looking at U of t. The mixing matrix would just be 0, 0, 1, 1, 1, and zeros. Okay, that would be non-negative. The other thing is that the U of t is a polynomial in the adjacency matrix, so it commutes with the adjacency matrix. And so that means this commutes with the adjacency matrix. And so that means in particular that the unsigned matrix -1 times this is an automorphism of P3. Now it's the obvious automorphism. It swaps the first and last vertices. And we'll see things like this happening again. It doesn't always happen, but it happens on occasion. So it's not important what we're about to do, but the point simply is that U of t is a polynomial A, and therefore it always commutes with the adjacency matrix. And so if it has a special form, it's telling you something about the adjacency matrix. And so in this case, it's telling you that this graph has an automorphism swapping vertex 1 and vertex 3, which you don't need quantum walks to tell you. And you can check that at time pi root 2 that the U of t is the identity. Okay, so and pi so pi root 2 is twice pi and root 2, and so again we have PSD as said at the time pi and root 2, and twice that we get periodicity. Okay, so that's 2 examples. We go on. The first thing I want to do is explain the relation between where the periodicity is coming from. So the way I say the theorem is if a graph emits perfect transfer from A to B at time tau, it emits perfect state transfer from B to A at time tau. Now, be very careful here. We're not saying that both these things happen at the same time. We're saying that if you start at A, then at time tau you're on B. And if you start at B, then at time tau you're on A. Okay. So the proof is straightforward. So if we start on A and at time tau, this is our state, and we want that to be equal to EB transpose. And all I need to do is take complex conjugates of everything inside. Now, this is a real matrix, so this stays where it is. I have complex and this is real, so it doesn't change. So I get complex conjugate of U of t, complex conjugate of U of minus t, but the complex conjugate of U of t is U of minus t. And the complex conjugate of U of minus t is U of t. So we get this equal to this. And now we just pull VUs over to the left, and you get U tau, EB transpose U of minus tau is equal to EA transpose. So this gives you a proof that if you have PSD from A to B at time tau, then you get PSD from B to A at time tau. Now, one thing that's important to note here is what properties of these states have we used? And I claim the only property the states we've used is that the matrices are real. Okay, so there's something much more general is true. We don't need it for now, so I won't go into it. But the only property of the density matrices I've used is they're real. Okay, and so if you come up with other states that are real, then you're still going to get this property. The other comment, of course, is if you get if you have PSD from A to B at time tau, and then you restart on B, then at time and wait another tau, you're back on A. So this tells you that if you have PSD from A to B at time tau, you're periodic with time 2 tau. So this implies periodicity. And again, we don't really need much in the way of properties of the state. But I'll come back to that, but for the moment. So if we have PSD from A to B, we have PSD from B to A. And if we have PSD from A to B at time tau, then we're periodic at time 2 tau. Okay, and this is useful for us in our research because when we're looking for examples, we usually look for periodic vertices first and then test which of those are going to give rise to perfect state transfer, apart from being an interesting mathematical property. There's a second proof of this result, which is simply to note that to get PSD, you want a certain entry of MFT to be equal to 1. You want the BA entry to be equal to 1, but MFT is symmetric. So if the BA entry is 1, then the AB entry is 1. And if the BA entry is 1, you have PSD from B to A. So the second proof is simply the observation that MFT is symmetric and a few moments thought. Okay, which is, and so the advantage of this proof is that it holds it more generally. But either way, we get it. Now, still, that's all well and good, but we really like to have more than 2 examples of perfect state transfer. And the tool here is products. Now, one of the 2 basic principles of quantum mechanics is if you have each quantum system is given by a state space, and a composite quantum system is given by the tensor product of the state spaces. Now, the simple setup is you have Alice working at her bench, experimenting with some walk on some graph, and Bob working on his bench with some walk on some graph. And you can think about the outcome of their joint outcomes. And so you have a composite system, and to actually do the analysis, you have to assume that the state that they're working on is the tensor product of Alice's state with Bob's state. Okay, so tensor products correspond to composite systems. And so if I'm working on some graph and you're working on some graph, then the joint system is given by the Kronecker product of the Kronecker product of the entries. Now, the key observation is that the continuous walk on a Cartesian product of X and Y is just, well, the transition matrix, that is just the Kronecker product of the continuous walk on X and the continuous walk on Y. Now, the proof of that was one of the assignment questions. Okay, so we've done that. And so we have this thing. So the point is on the right-hand side, we have a kind of physical statement. This is a composite system. On the left-hand side, we're seeing that composition corresponds to Cartesian products. And so this is why Cartesian products are useful in dealing with quantum walks. Now, and so if you're bored, you've got your machine working with K2, you could buy, and you're getting bored, you could buy a second machine or a third machine. So you have 3 copies of K2, and now the underlying state space would be the Kronecker tensor product of the 3 two-dimensional states of the 3 states corresponding to each of those things. Now, the key thing here is that if X has PSD from U to V at time tau, and Y has PSD from W to X, that should be a tau too. Let's fix it. Time tau. Then the Cartesian product has PSD from this ordered pair to that ordered pair at time tau. Now I'm leaving that as an exercise, but it's not difficult at all. So the point is that if I have 2 graphs and I get perfect state transfer, perfect state transfer on each graph at the same time, then on the Cartesian product, I get PSD from one ordered pair to the other ordered pair of vertices. Okay, and so one consequence of this is, for example, the Cartesian power of K2s will admit perfect state transfer. Now, the Cartesian power of complete graphs on 2 vertices is of D copies of the complete graph on 2 vertices is the D cube. Okay, And so a corollary of this is that the D cube has perfect state transfer from the 0 vector to the all ones vector at time pi and 2. Now you have to do a little work to get the pi and 2, but you get the, well, no, we don't have to do any work because we know that we have PSD from one vertex to another at time pi and 2 on K2. And so when we take D copies of it, we're still going to get PSD. If each bench starts on the state 0, then at time pi and 2, they're each in state 1. Okay, and so we get now have an infinite family of examples of graphs on which perfect state transfer occurs. And I mean, the cube is not the worst graph. If you had to use in practice, it's comparatively sparse. The valency of the vertices is a log of the number of edges. The valency of the vertex is a portion of the log of the number of vertices. So it's not a dense graph in any sense. And you know, the difficulty of implementation is going to be depend in part on the number of edges of your graph. So it's not, this is not a useless example by any means. Okay. Also, many of our constructions later of other examples of perfect state transfer in some sense come from the cube. Any questions about this? Similarly, the Cartesian power of the path and tree vertices has diameter 2D. That's in the notes as that's in one of the assignment as an exercise. It's not very difficult, but it's a useful result. And so it then follows that the Cartesian power of the D3 path on 3 vertices has perfect state transfer between pairs of vertices at distance 2D. So actually, let me. So if we take P3 times P3, then we're getting perfect state transfer between this vertex and this vertex. Ah, damn. And similarly, we get perfect state transfer between that vertex and that vertex. So those two vertices I just indicated are at distance 4. Okay. So now we have 2 infinite families. Okay, using the Cartesian product. I find it quite interesting that the composite systems are tensor products. The graphs, the composite quantum walks will be walks on Cartesian products. So it makes the Cartesian product more interesting. Now I mentioned the other. I said the 2 interesting phenomena were perfect state transfer, which is in some sense the most interesting. But the other issue is what I call uniform mixing. We say the graph has uniform mixing at time tau if there's local uniform mixing at time tau from each vertex. Now, this is equivalent to the assertion that at time tau, the unity matrix, all its entries have the same absolute value. And so that is what I'm calling flat. So that we have uniform mixing if U of t is flat. We have local uniform mixing if some column of U of t is flat. Okay. Now, the uniform mixing is interesting combinatorially because we're getting a flat unity matrices, and these have a number of combinatorial consequences. And local uniform mixing already is fine. So we're having a column of MT is flat. And the theorem is that if X and Y have uniform mixing at time tau, then so does their Cartesian product. And it's the same proof as before. We use the fact that Cartesian products correspond to tensor products of transition matrices. And so using K2, so in other words, we're going to get uniform mixing on the D cube. Okay, and so we have infinitely many examples of D cube. Well, it's natural to say, well, we've done path on 2 vertices and the path on 3 vertices. What about the path on 4 vertices? Well, you'll have to wait. The answer is more complicated. Turns out there are difficulties. The next easy case to work with are the complete graphs. and now Hermie was talking about this morning, it's probably possible to work out the transition matrix for the complete graph using the power series, but it's certainly easier to use the spectral decomposition. Now, the complete graphs, Kn, this adjacency matrix is the all-ones matrix, take away the identity. The eigenvalues of J are n with multiplicity 1 and 0 with multiplicity n minus 1. And so the eigenvalues of this are n minus 1 with multiplicity 1 and minus 1 with multiplicity n minus 1. And this superscript in parentheses notation is what I sometimes use to denote multiplicities. Okay, so the all-ones vector is an eigenvector for the eigenvalue, simple eigenvalue n minus 1. So we take the outer product, we get that the idempotent 1 on n times j. And we don't need to do any more calculation really, because the sum of the idempotents is the identity. There's only one more identity, so it must be this. Okay, so we have the spectral decomposition of A, and we have the spectral decomposition of U of T. Okay, so we have a formula there. And to get something out of it, we just need some minor rearrangements. There's kind of a common factor of e to the minus it, so I've pulled that out. And so if I do that, I get this. And then I can write it in this form. So U of T is this. Now, as I said, to understand what's actually happening from experiment, that's not the entries of U of T of matter, it's the entries, it's the absolute values of the entries of U of T. When you take absolute values of the entries of U of T, this plays absolutely no role. Its absolute value is 1. Okay, so it's just this part that matters. And the second thing is e to the nit. Well, it's somewhere between, absolute value lies between 1 and minus 1. And so the absolute value of e to the nit minus 1 is at most 2. And so the absolute value of this is at most 2 on n times the all-ones vector. So the off-diagonal entries of U of T are bounded above by 2 on n. And so as n goes to infinity, the mixing matrix converges to the identity. Now, what this means, if you have a continuous quantum walk on a large complete graph, and you start on vertex A, and you look at it sometime t, you'll discover with high probability you where you started. And it doesn't matter which vertex. So this is quite counterintuitive. When I point this out to some physicists, they're quite surprised. And I have the pleasure of saying it's quantum mechanics, it's hard to understand. So the point is that for a large complete graph, the continuous walk, in a sense, the vertices stay at home. And so I say this is complete graphs are sedentary. So for the large values of n with high probability, the quantum walker stays where they start. And so you can't get perfect state transfer on a large complete graph because you would need an off-diagonal entry of m of t to be 1. But the off-diagonal entries are going to 0. So there's no perfect state transfer. And similarly, look at that. So this is a surprising property of the complete graph. Okay, I mean, the point is, if you have an ordinary continuous random walk on a graph, now in that case, you're on a vertex, and in a time interval delta t, you move to one of your neighbors with probability one over the number of neighbors times delta t. So you move to one of your neighbors, and the probability that you move is proportional to the length of the time interval. Now, in that setup, you get a continuous walk on a graph. And in that setup, the state spreads out. And so in the end, you're equally likely to be on any vertex, no matter where you start. So in a classical random walk on a graph, a complete graph, everything smears out. That's not what happens in a quantum walk. So this is interesting, probably the complete graph, and there's also an important difference between the classical case and the quantum case. And as I said, even some of the physicists I mentioned do find this surprising. Going over time. Okay, so I need to talk a bit about bipartite graphs. This is standard graph theory, but you may not have all seen it, and it won't hurt to review it. Well, for example, we've done the complete graphs. At some point, someone's going to say, what about the complete bipartite graphs? But so let's talk about bipartite graphs for a bit. Now, the graph's bipartite, there's a partition of its vertices in two classes, each of which is a co-clique. Core B class is a color class. And so you can write the adjacency matrix in this partition form. So B is not square in general. Okay, so for give a trivial example. So for P3, you get that. So and so we get this. But any bipartite graph, the adjacency matrix can be written in this form. Now, this has an important consequence that if X is bipartite, then the adjacency matrix and minus the adjacency matrix are similar. So A and minus A have the same eigenvalues, and so the eigenvalues of A are symmetric about 0. Okay, there's various ways of proving this, but I think this is proving that fact that this is the slickest. So all I do, well, I want to prove they're similar. The obvious way to do is to write down the similarity matrix, which does a similarity transformation. It's not difficult. It's minus I. Now this is self-inverse, so this is matrix, adjacency matrix minus matrix to the inverse. And so when you do the calculation, you get exactly this. And so this is a similarity transformation, says this is similar to this. And so the conclusion then is if X is bipartite and theta is an eigenvalue of X, then theta is an eigenvalue with the same multiplicity. So for the path on three vertices, we saw the eigenvalues were minus root 2, 0, and root 2. So they're symmetric about the origin. Okay. And in this case, they're all simple. Now, you'll also see, for example, if you have a bipartite graph on odd numbered vertices, then it must have 0 as an eigenvalue. But that's not going to help us that much. Now, we can actually go a little bit further. We can actually get the eigenvectors. And so the assumption here is, okay, suppose I've got an eigenvector. I'm going to write it in partition formed X and Y. So this is a function of the vertices. X is on the white vertices, Y is on the black vertices. So this is an eigenvector. So this times this must be theta times this. Now, that means that if you multiply this out, you get that theta xy is equal to by. So you've got a by and a b transpose x. Now, if you apply this to x minus y, you get minus theta times x minus y. So what I'm saying here is that if xy is an eigenvector for the adjacency matrix of bipartite graph with eigenvalue theta, then x minus y is an eigenvector with eigenvalue minus theta. So you can actually, if you have an eigenvector for an bipartite graph with positive eigenvalue, you can write down a corresponding eigenvector with negative eigenvalue. Okay, and that's in some sense, that's also a consequence of this, but I've just written out directly. Now, you can actually, I don't know, spend any time on this, you can relate the spectral idempotence of spectral idempotent belonging to theta with the spectral idempotent belonging to minus theta. And that's worked out there, and I think I'll just assume you're going to read that. How much more about this? Plenty. Of course, if we're thinking about bipartite graphs, we want to do continuous quantum walks, and so I need to compute the exponential of IAT. Now, the point here is that if I take U of t and apply the same similarity transformation I've been using before, I get this. Okay, and so if U of t has got this form, so if this is this, then you get this. So if these two things are equal, you're getting U0, 0. And so, well, the point is that this is equal to this is U inverse. Okay. And so the conclusion you get is that the diagonal blocks are real, and the off-diagonal blocks, you can write they're I times the skew symmetric matrix. And so the conclusion, let me miss this, is that if X is bipartite, then the U of T can be written in this form, where C1 and C2 are real, and S is skew symmetric. Well, actually, it doesn't matter, and S is real. That's what we need. So that the transition matrix for a bipartite graph has a special form. In particular, the entries are either real or purely imaginary. And that's what I'll need. Actually, I think this is where I'll stop. So we're going to use this to get some information about when uniform mixing can occur on bipartite graphs. Okay, and it turns out there's a connection to Hadamard matrices, which are important objects in combinatorics. But so we will see a connection to Hadamard matrices, and from that we'll get some information about uniform mixing on bipartite graphs. But I'll stop there for today.